We're in the packet, and we're going to do a bunch of problems in the packet. And what we're trying to do right now is make sure that we're comfortable with moments and using the right-hand rule. So I'm going to pull this up. I'm going to do this. Okay, so we're talking about torques, and I'm just using that word for the last time now, because as engineers we use the word moments instead. Okay, and there are two different ways to solve for a moment. So what are the two different ways you can solve for a moment? In the end, once you have the moments, then we can sum them all up and say that they're equal to 0, so that we're saying that there's no rotation. But how do we calculate the moment? What's the unit of a moment? What's the unit? Okay, Newton meters. So one example is Newton meters. What's another one?
Foot pounds.
Foot pounds. Isn't this kind of interesting? What do you notice? So this is really, a moment is equal to a force times the distance, right? Isn't it interesting in metric? We use Newton meter, we put the force first. And in English system, we say foot pound, we have the distance first. Okay? We need to be comfortable with those terminologies, so that in the metric system, we always say the force first. So what's another one? Kilonewton meter. Right? How about Newton millimeter? Kilonewton millimeter. Okay, so in metric we always put the force first, but in English we put the distance first. So give me another example besides foot pound.
Inch pounds.
Okay, inch pound. What else? What was that new one we learned, that word for 1,000 pounds? Kip. So how about inch kip? Or a foot kip? So what we're doing is we're multiplying our force times the distance. And there are two different ways to solve for them. Which ways have you done it? How about this? Cross product. Great. So vectorially, you solve for it, and it was a cross product. It's R cross F. And the other way was, what's this? What's that stand for? RHR, right hand rule. So two different ways. We're going to start out using right-hand rule, then we're going to go towards vectors, then we're going to go into 3D. So we're going to start with 2D right-hand rule, 2D vectors, we're going to go to 3D vectors, and then we're going to go to 3D right-hand rule. 2/3 through this course, you're going to be so comfortable with using the right-hand rule in 3 dimensions that you're not going to use vectors. Because take a look at the tripod right there. If I wanted to know what moment this camera is causing on each of those legs, I don't want to have to sit down and start writing out vectors and doing a cross product using matrices. I want to be able to look at that and say, oh, the force is here, the weight of it's here, it's going to cause it to turn that way, and it's going to spill towards Kyle. I want to be able to physically be able to see what kind of possible moment it could have. Okay. So let's start out with 2D right-hand rules. So we're looking at this over here. There are two different ways that you guys use do the right-hand rule. The way I do it, and I want you all to do it this way first. If I'm trying to find the moment about point A. So here's point A. I'm trying to find the moment about point A. I put my fingers in the direction of the force. Put my fingers in the direction of the force. I put my palm towards A. And this is how it's going to spin. And my thumb is coming out. So is it going to be a positive or a negative moment? Positive. Positive. So our positive designation is this. If it goes counterclockwise, it's positive. And that's what you used in physics, right? Counterclockwise was positive. So we're not going to have to write that little symbol anymore. As long as you give me a positive value in 2D, I'm going to know which way it's spinning. So again, right hand, fingers go in the direction of the force, palm goes towards point A. Some of you put your fingers in the R, in the direction of the lever arm, the distance, and then you put your palm towards the direction of the force. Either one would work, but I'm always going to do it because to me, what's the most important is the force. We're talking about statics. Statics is the study of forces on bodies, so force is really the subject of my sentence, and the distance just tells me how much my moment can be. So for me, my fingers are the most important, and I put it in the direction of force, and my palm towards the point. So going back to right-hand rule, how do you calculate the moment? What's it equal to? Right-hand rule, what do I multiply by what? The force times the distance. And it's the absolute value. Are you guys comfortable with this, or do you like the double? It's the absolute value. It's the magnitude of the force times the magnitude of the distance. So when you use the right-hand rule, it's the magnitude of the force times the magnitude of the distance. But a moment has direction, right? We know it's a vector. Is it spinning to the left or is it spinning to the right? So how do I figure out the direction? The direction I figure out, whether it's positive or negative, I figure out by using my right hand. And we already said that if it's counterclockwise, it's positive. If it's clockwise, it's negative. So let's look at this example right here. I'm trying to find the moment about point A. Using the right-hand rule, which is what we're doing here, it's the force, 100, times the distance. And the distance here, it's important to note that this is the perpendicular distance. It's got to be the perpendicular distance. What's the perpendicular distance between the force and point A? 5. Because the force is going up in this direction. Here is where it's perpendicular. This is the perpendicular distance. So it's 100 times 5, which gives me 500. And the units are, is it inch pound or pound inch? Inch pound. Because in the English system, we put the distance first. And now we have to, so we have our magnitude, but we didn't do our direction. So fingers go in the direction of the force, palm goes towards A. What do I get, a positive or a negative? Positive. You don't have to write positive, but I'll write it. Okay, so we're going to start going around the room now. Wes? So now I'm trying to find the moment about point B. So tell me what I need to do here.
Fingers in the direction of the force.
Okay?
100 times 10.
100 times 10. So 100 is the force, 10 is the perpendicular distance, which gives me 1,000. What's the units?
Inch pound.
Inch pound. And tell me now, using the right-hand rule, do you get a positive or a negative?
Negative.
Negative. Everybody good? Okay, Karen, next one. Let's go to number 2 now. We're finding the moment about point A. So what do I multiply by what?
150
150 times?
times 5 inches.
Okay, so take a look at this. This is always the confusing part. Here's my force. My force is going along this direction, right? So where is the perpendicular distance? This
Seven.
right here is gonna be the perpendicular distance, right? So what is it?
7.
Right. So 150 times 7, what was the number?
100 or 1,050.
1,050? Thanks. And what units, Karen?
Inches, pounds,
Right? And did you get positive or negative?
positive.
Finger, everybody, fingers go in the direction of the force, palm goes towards point A, I got a positive. Okay, Peter, next one, B.
Pass.
Okay, Paul?
Oh, B?
Yeah.
Okay.
The force
So,
is,
Force is 150,
okay, perpendicular
or,
distance,
if you want to go for perpendicular distance would be, I think we're still at 7.
that's right. Does everybody see that? It's still the perpendicular distance. Everybody look up here, anywhere along line AB is gonna have a perpendicular distance of 7 to that force. So that's 1050 again, what units?
Inch, pound,
Right, and is it positive or negative?
positive.
Positive.
Oh, it's positive?
Yeah, so fingers still go in the direction of the force, and the
Oh.
palm goes towards the point, it's still positive.
Oh.
So what you're doing is you're looking at a rotation. Do you remember a pinwheel? You know, those things, you know, plastic has blades, you blow it and it spins around and that's a pin. So what I'm doing is, really what you're doing is, for the first one, make believe your pin is right here. And you're pulling the force here. Which way is it gonna spin? It's gonna spin that way. Now your pin is here, and I'm still pulling it this way. It's gonna still spin in the positive direction. Okay? Okay, Haley, third one.
Well, this is 150, but the perpendicular is 0.
Right, great.
So it's just 0.
Right. So the force is still 150, but the perpendicular distance is 0. And does that make sense? Look at this. Now I'm putting my pin right here, and I'm pulling it. Is it gonna have any rotation? No, the only thing that can happen is that I'm pulling it laterally. When we calculate moments, we're calculating the rotation that's being caused. Okay, if I go to push Pete, he's only gonna go this way, lateral, unless I push him like this, then he'll spin. I gotta be off the center to cause something to spin. Okay, let's look at 3. So Kyle, we're up to you.
So the force, 100 pounds.
Yeah, okay, so what Kyle's saying is, from here, we know that it's 100 pounds, right? And now the perpendicular distance, I'm gonna have to find what that perpendicular distance is, right? Okay, but we're not gonna do that. Can you think of something that we're very comfortable with doing? Because I don't wanna do the geometry. I don't wanna do the geometry to find out that perpendicular distance. Can you think of something we could do to the force where we know the distances already? Santiago?
Could you multiply the angle 30 times the force times the distance?
Tell me why you're using the angle.
Because
What are you trying to do to the force?
I'm trying to set up a vertical axis from point C,
Okay,
and so I will have to rotate downwards to A.
are you still trying, Santiago, are you still trying to find this distance by using that angle?
Yeah.
Let's not do that. Because Because it just makes it more complicated. There's something that we can do to the force that we're very comfortable with, where we don't have to find this distance. Jill, do you know what it is? Break it into components. We already know totally how to do that, right? If I say this is Fx and this is Fy, don't I then have the perpendicular distances? Right? So these two problems, I knew the perpendicular distance was given to me. This problem, the perpendicular distance isn't given, and you could probably find that perpendicular distance. For me, it's easy to break it up into components. So let's take a look at this instead. So what is the x component of 100? It's 100 times
Cosine 30.
cosine of 30. And think about this, remember, we're only trying to get magnitude. You guys look over here. We want the absolute value of it. The absolute value. Usually what we would do to find the x component, wouldn't we say 100 times 90 or 120, cosine of 120?
Yeah, it would be.
Right? That would be to get the negative, but we don't need the negative. We only need the magnitude. So 100 times the cosine of 30, is that the 86? Yeah, 86.6. 86.6 pounds. And the Fy is 100 times the cosine of 60, which is 50 pounds. So I just broke that force up into components because I could do that in my sleep. I've done it so many times. So now Isadora, let's look at Fx. Fx is 86.6, right? What's its perpendicular distance to A? 7. And does it create a positive or a negative? Positive. And then how about Fy? It's 50 times, what's the perpendicular distance to A still, Isadora? Here's the force. And what's the perpendicular distance to A? 5. And is it positive or negative? Positive. And it comes out to be 856.2. So let's look at that one again. We didn't know outright what the perpendicular distance was, but we're comfortable finding components. So we broke that 100-pound force into an Fx and an Fy. Once we got the Fx times the perpendicular distance to A, the perpendicular distance is 7, and we put our fingers in the direction of Fx. I put my palm towards A and a positive. Excuse me. Then Fy was 50. The perpendicular distance from Fy to A is 5. And it also creates a positive moment. Questions about calculating that one? Any questions?
It just seems like the magnitudes are really high for a 100-pound load. You're getting 850.
Can you figure out what the perpendicular distance is now?
Yeah, you're at 250.
So we know that the moment is equal to the force, absolute value of force, times the absolute value of the perpendicular distance, right? If we want to find the perpendicular distance, isn't it equal to the absolute value of the moment divided by the force? And we know the moment was 856.2. And we know the force was 100 pounds. So isn't this 8.56 inches? Does it make sense, taking a look at where that 100-pound force is, does it make sense that the moment created by that force is positive? We're trying to find the moment about point A, right? So point A here, this is where my pin is. I have my pin here, and I'm taking this force and pulling it. Shouldn't it create a positive moment,
Yeah.
right? You guys with me? Yeah? Okay. So let's do, Andrew, we're up to you. Let's do a moment now about point B. We still have the same force, we still don't know what that perpendicular distance is, so we're gonna break it up into components. So it's 86.6, what's the perpendicular distance to B of Fx? Number. Fx is right like this, right? So what's the perpendicular distance from Fx to B? 7. Does everybody see that? This is the perpendicular distance right here. Does the Fx, Andrew, create a positive or negative moment about B?
Positive.
Positive. Okay, and then Jill, the y is a 50. Jill P, so it's 50 times, what's its perpendicular distance? Here's Fy, 10. And does it create a positive or a negative moment? Put your fingers in the direction of force. Fingers direct, palm goes towards B. What do you get, a positive or a negative? So let's do that one again. So fingers go in the direction of force. Palm has to go towards point B. So I'm getting a negative. And doesn't it make sense if my pin is here and my force is being pulled up that way, it's going to spin clockwise, which is negative. So this is a negative. And what does that turn out to be? 106.2. 106.2 inch-pound, and it's positive. So, Chris L., the fact that we found that the moment about point B, due to that force, is positive, does that force of 100 pounds, is it above B or below B? So let me ask that question again before you answer it. Hang on. What does this NTS stand for? Not to scale. It's an excuse for not drawing something to scale, right? It gives me leeway. So because it's not drawn to scale, we don't know if this 100-pound force is above B. Is it going like this? Or actually, since it's not drawn to scale, should it actually be going below B? So the fact that we see that the moment about B is a positive value, that's not a very good plus. A positive value, does this force, Chris, lie here or here? Above B or below?
I'm not sure. Positive means it's counterclockwise.
Okay, so show me with your hand how it's spinning.
It's going to be spinning this way.
It's got to be spinning this way.
So it would be above.
It would be above. Because if the pin is here, in order for it to spin counterclockwise, the force has to be here, right? Because if the force was down here, show me, your fingers would go in the direction of force, but the palm has to be towards B, it would be a clockwise spin. This force has to go above B.
Oh, okay.
Okay, and Evan, what's the perpendicular distance? So Evan, so we know the moment is equal to the absolute value of the force times the absolute value of the perpendicular distance. So the perpendicular distance is going to be the moment divided by the force. And what's the moment we calculated for B?
106.2.
106.2, and what was the force?
50 pounds.
No, the total force. 50 was only the Y component, right?
100.
100. So the perpendicular distance is 1.06 inches. So this force is like this, where the perpendicular distance, this distance right here, is 1.06. That's the perpendicular distance right there. So the force is going like this, and here's the 1.06 to where B is, perpendicular distance. Okay, let's do another one. Oh, we didn't do the last one. Or G, what's the moment about point C?
You break it up into components again, but there's no perpendicular arm, so
There's
it'd be zero.
there's no arm, there's no lever arm, so it's equal to
0.
0. The moment about point C is 0 because the force goes through point C. Okay, the next one we're going to do is on page 16 in the packet. And why don't you work with the person next to you? And what I want you to do is figure out the moment about point. Figure out the moment about point O. Does everybody see where point O is? Here's point O. And let me also say that, draw these two little perpendicular marks here. So this case, you have three forces, F1, F2, and F3. They all create a moment about point O, or potentially. So let's write it like this. The moment about point O due to F1 is this. The moment about point O due to F2 is this. And the moment about point O due to F3 is this. And then the total moment about point O would be the addition of all of them.